The Faraday's Electromagnetic Lab simulation is an interactive educational tool designed to help students understand and explore Faraday's law of induction, a fundamental principle in electromagnetism. This simulation allows students to experiment with magnets and coils, providing a hands on approach to learning about the relationship between changing magnetic fields and induced electric currents. The simulation is divided into several parts: the pickup coil, electromagnet, transformer, and generator, each offering unique insights into different aspects of electromagnetism. The pickup coil part of the simulation allows students to move a magnet through a coil to induce an electric current. By moving the magnet in and out of the coil, students can observe how the changing magnetic field induces a current in the coil. This interactive feature helps students understand the concept of electromagnetic induction and the generation of an electromotive force. Students can vary the parameters of the magnet and the coil to observe how these changes affect the induced current. For example, they can adjust the strength of the magnet, the number of turns in the coil, and the speed at which the magnet is moved. These adjustments allow students to explore how different factors influence the magnitude of the induced EMF. The simulation includes a voltmeter and a light bulb to measure the induced EMF. By connecting the voltmeter to the coil, students can directly observe the voltage generated by the changing magnetic field. The light bulb provides a visual indication of the induced current, with the brightness of the bulb corresponding to the strength of the current. This feature helps students understand the practical application of Faraday's law in generating electricity. The electromagnet part of the simulation allows students to use a battery to create a magnetic field. By connecting a battery to a coil, students can observe how an electric current generates a magnetic field. This interactive feature helps students understand the concept of electromagnetism and the relationship between electric current and magnetic fields. Students can experiment with different ways to make the magnetic field stronger. For example, they can increase the number of turns in the coil or increase the current flowing through the coil. These adjustments help students understand the relationship between the strength of the magnetic field and the parameters of the coil and current. The simulation also allows students to experiment with an AC, alternating current, source to create an oscillating magnetic field. By switching from a DC, direct current source to an AC source, students can observe how the magnetic field changes direction rapidly, oscillating between two polarities. This feature helps students understand the concept of alternating current and its application in generating oscillating magnetic fields, which is fundamental to many electrical devices and technologies. The transformer part of the simulation allows students to explore the principles of voltage transformation. By using an electromagnet to create a magnetic field and a pickup coil to detect the induced EMF, students can observe how the voltage can be transformed from one value to another. This interactive feature helps students understand the concept of transformers and their role in electrical systems. Students can explore the many parameters that create a change in the magnetic flux to produce a signal in the pickup coil. For example, they can adjust the number of turns in the primary and secondary coils, the strength of the magnetic field, and the frequency of the AC source. These adjustments help students understand how different factors influence the transformation of voltage. The generator part of the simulation allows students to discover the principles of an electrical generator. By rotating a magnet within a coil, students can observe how the changing magnetic field induces an electric current in the coil. This interactive feature helps students understand the concept of electromagnetic induction and the generation of electricity. Students can experiment with different ways to maximize the brightness of the bulb connected to the generator. For example, they can adjust the speed of the magnet's rotation, the strength of the magnet, and the number of turns in the coil. These adjustments help students understand the factors that influence the efficiency of an electrical generator. The simulation provides an interactive platform where students can actively engage with the concepts of electromagnetism and Faraday's law. By adjusting various parameters, students can see the immediate effects of their changes, reinforcing their understanding through hands-on exploration. The visual nature of the simulation makes abstract concepts more tangible. Students can observe the changing magnetic fields, the induced currents, and the transformation of voltage in real time, helping them to grasp complex ideas more easily. The simulation offers immediate feedback, allowing students to see the results of their experiments instantly. This helps correct misunderstandings quickly and reinforces learning through trial and error. The simulation is flexible, allowing students to explore a wide range of scenarios. Whether investigating the pickup coil, electromagnet, transformer, or generator, the simulation provides a comprehensive learning experience. The Faraday's electromagnetic lab simulation is a valuable tool for teaching and learning about the principles of electromagnetism and Faraday's law of induction. By providing an interactive, visual, and flexible platform, it helps students understand the fundamental concepts of electromagnetic induction, electromagnets, transformers, and electrical generators. Whether used in a classroom setting or for individual study, this simulation can significantly enhance the learning experience and build a strong foundation in physics and electrical engineering. Through exploration and experimentation, students can gain a deeper appreciation for the complex and fascinating interactions between electricity and magnetism.